Swayam Prabha. Digital India. Educated India.
Yeah, so what you want is you want those compositions which have high hardness but a particular element is not present, right? Or a particular element is of low concentration. So see, machine learning model allows you to make prediction for everything, right? So something that the word that I like to use is candidate set. So you have a candidate set for which you want to make prediction. Okay. In your case, the candidate set can only be those alloys which have a low concentration of that particular element. Only for those alloys you go ahead and make the prediction and you check whether any of those have a high hardness or not.
Even such a candidate set is absent, or rather the candidate set is actually composed of the converse.
As I didn't get your point, sorry.
Even such a candidate set is not present.
The candidate set should be present. The candidate set should be present because candidate set is something like on which you want to make a prediction. See, once you have built a model, you will use it to make prediction on something, right? I'm calling that something as the candidate set. What you are using a model on, that is the candidate set. Okay.
We may not have, like, say, entire data may be based upon some element which we may not be targeting that element at all.
Yeah. So his point is, okay, we'll come to this point. Okay, in this session itself, we'll try and come to this point. Okay, so next thing I want to talk about is just the fingerprints, the features. Okay, so features being people who here are more from domain knowledge experts, meaning material scientists, people from physics background, chemistry background, science background. So this is something that we will relate the most to as part of this complete machine learning pipeline. Okay. So what is going as input to the model is basically your features or fingerprint. Okay. And now in this entire session, we'll try to understand what is the best way of coming up with this fingerprint. Okay, that's what this session is about. Now, depending on the data set, obviously the fingerprint will be of different types, but we'll try to come up with a general structure by which we can create new fingerprints and so on. Okay. So, remember this from the last session, we need 4 stages. First, we need to collect data, then we need to fingerprint them, some machine learning model, and then making prediction. Okay. Now, here I am giving some examples of how a data set may look like. Okay. This example we already did. We talked about few alloys and then their hardness. But a data set may also be something like this, wherein you have different polymers and their associated lithium-ion conductivity. Something like the solid state conductor lithium-ion electrolyte example I gave. Okay. Now, how do these polymers are different? It could be chemically, monomer wise they are different. The monomer chemistry itself is different. It may be that it is the same monomer chemistry, but it depends on what is their molecular weight, okay, their polymer dispersivity index, whether they are different or same, things like that. Okay. Another way my data set could be, I have set of TEM or SEM images, and for those images I know this is how the mechanical properties of those alloy are. Okay. So this is how a data set may also be. It not necessarily be your this composition and that thing. It could be a set of images, and associated with that I know this is how my mechanical properties are. A data set may also be something like this, where I have different processing conditions, same chemistry, different processing conditions, and associated with different heat treatment, associated with different forming conditions, I am getting a different structure, image. Okay, microstructure is different. Now I'm in my output is something like a image. Okay, so all of these are different types of data set that you can imagine, and I mean that figure that we have, right? Property, structure, processing. What else is there? Composition? No. Performance, right? So I think you may want to, properties and performance, maybe we can club them together somehow. But structure, with structure, whether it is chemical composition based, whether it is microstructure and image data, okay, or and then processing is somehow covered here. All of these could be input and output. That's what I'm trying to convey. Okay. And now for these different cases, we need to learn what is a good fingerprinting strategy. Okay. By the way, image, how do you store an image? What is image? What does an image mean? Yeah, basically image is nothing like, but it's something like a matrix only, right? It's at every grid point, at every cell, you have some number. It could be a RGB number, it could be a grayscale image, but at every point you have some number. So basically it is something like a matrix. Okay. Okay. So now just giving you some idea, we will recollect that fingerprint is nothing but a numerical representation. Okay, I need to come up with a bunch of numbers which are telling me that this is my attributes of my material or for my image, whatever it is, and it's a large dimensional vector. Okay. Now, what are general considerations for a good fingerprint? So, one important thing is, see, anytime you are making a model, you want to use it for making a prediction. Later, downstream, you want to use it for making a prediction. So, you want to come up with those fingerprinting strategies which are easy to compute. It should not be that I am using something as a fingerprint which is very difficult to even compute. So, say there is a fingerprint in which I need an XRD done on the sample. Say XRD is my numerical representation. I think Kamal also gave this example yesterday. So if I'm using XRD for a new material, if I have to go through this whole process of making the material, getting its XRD, it's a very expensive way to just come up with a new fingerprint, right? So it defeats the purpose of doing machine learning in a very high throughput manner. Okay. So you always want to consider those fingerprints which are very easy to compute. Something based on atomic structure, things like that, atomic bonding. These are things which can be easily computed. Another important thing is the fingerprint should be unique. In this example, this is my fingerprint for first data point, fingerprint for second data point. These two should be unique. If they are not unique, what does it mean? This vector and this vector are same, but the properties that these two have is different, which means you can never come up with a function that will map one fingerprint. Same fingerprint, it cannot map to two things, right? Two outputs it cannot map. So I should always look for fingerprinting strategies which are able to uniquely represent my material or processing condition. Will not be able to go into detail of the third point, but the simpler your fingerprint, the lower the dimensionality of your fingerprint, the better the learning may happen. Okay. Basically, you have to look for a simplest enough representation of your material to be able to do good learning. Okay.
But many times, number of features are large in number, and the rows of data are less.
So that's why I carefully choose the word simplest enough representation. So you want to have large number so that enough information is there, but at the same time you do not want to have repetitive information being present and then try to simplify as much as possible. PCA also, whenever you do, you lose some information. Okay, you can talk about how much variance is captured by my PCA features. So people talk about 95% variance is captured and things like that. 5% is left out. Whether that 5% is important or not, we need to judge. Usually it's a good strategy, it's considered to be a good strategy that you cover 90% or 95% variance of your data and then leave out the rest. But you still need to make a judgment whether leaving out that 5 or 10% is it good or not. Sometimes even that can affect your accuracy of your model. So we'll have an exercise of, next we'll do an exercise of creating alloy fingerprints and polymer fingerprints. Then I'll ask you. Okay. Okay. Another thing, I'm just giving you overall hints, and what we'll do next is, we will do an exercise of creating fingerprint, and then we'll go through this list again to check whether we all followed this list or not. Okay. So next what we need to do is, we need to come up with a fingerprint that captures the invariance in the data, or equivariance, will leave that part. So some types of symmetries or some type of physical, some type of structure is always present in my data. So for example, DFT calculation you do on a molecule or a material, right? Say I'm talking about energy of a molecule or a material. If I just rotate my system, will the energy change? Energy should be fixed. So my fingerprints should be such that they recognize that it is simply a rotation, and my function should be invariant to this rotation of molecule or material. Okay. So either the fingerprint has to be invariant or the model has to be invariant. One of this thing I need to do to impose and understand that this rotation has no meaning in terms of energy of the system. Okay. This rotation will have meaning in the context of forces, because force vector will change. But force vector will also change according to the how much rotation you have done. Okay. Say one molecule was along the x-axis and it was stretched. Now I rotated and made it along the y-axis. Now the forces are along, it is still stretched, but now the forces are along the y direction, right? Earlier it was along the x direction. So energy is the same, but the force vector has changed. But it has also changed in a very neat fashion where the magnitude of the forces will be the same. So this thing is called equivariance, and somehow my fingerprint should be able to recognize this thing. Okay. So this one is a little more advanced concept, but I'm just laying it out there. And then you also want to think of, whenever you are designing a fingerprint, think of the underlying mechanism. Ultimately, your fingerprint, what your model is doing is mapping your fingerprints to the output property. So if you are able to capture the mechanism, whatever is the underlying mechanism, that you need to map it to the target property. So for example, again, if I am talking about energies, I know my distance between the atoms should be important. Electrostatic repulsions, attraction, this is what is contributing to my energy, right? So that distances is important. Dihedral angles are important. Actually, you can go to order of 2, 3, 4, 5. All these interactions are important and ultimately resulting in the final energy that you have. So this way, you can think of what are my features which are contributing to my target property, and you need to think of that, okay, if I'm able to think of a mechanism, then associated with that mechanism, these are the attributes which will help me learn the property. Requires domain expertise. Obviously, it requires mechanism, like you should have a mechanistic understanding of what is happening, and that's when you will be able to come up with better fingerprints. Okay. And last but not, I mean, that's a very important point. You can skip all of the points above and you can simply think of letting the model learn the fingerprints for you. Okay. So whenever computer scientists enter into the space of learning materials properties, they try to do this. Okay. In my opinion, I mean, the best examples of the successful models that you will see is done by neither material scientist alone nor computer scientist alone, but a merger of these two. So using some way of these above 5 points, 5-6 points, along with the last point, has resulted in some of the most accurate models that we are seeing right now. So some type of domain knowledge constraint, at the same time some learning happening from the machine learning models, that's where we are seeing, okay, which means now we need to have 2 degrees rather than 1. Okay, so I think I will come back to this later, but let's do this exercise wherein we already went through this example, right? These are my alloys, this is the hardness, say this is my data set. Now tell me, what do you think should be the fingerprint of my for this particular data set? Okay, so I'll just make some space. And I will write down what do you guys think should be my features for this data set. Yeah.
Like we do one hot encoding, maybe we can come up with multiple features where one correspond to aluminum, chromium.
Okay, one hot encoding. Okay, so I'll write it here. So people who may not be familiar, one hot encoding is, say I write down all my elements. Say I'm talking about only 10 elements, mostly the 3D transition elements. So aluminum, nickel, cobalt, something like this. And I simply make, I record. So for example, let me take this aluminum, chromium, iron. What else? Did I miss anything? Copper. Okay. Yeah. So for one hot encoding of this, for the first case, aluminum is there, so 1. Chromium is, nickel is there, so 1. Cobalt is there, no, so 0. Chromium is there, iron is there, copper is there. Did I repeat? Correct? So this is the one hot encoding of the first case. Okay. Okay. I will now simply write down whatever you say. We'll then discuss whether it's a good fingerprint or a bad fingerprint. So please tell me what else. Okay, one by one. So ionic radius. So ionic radius of so in first case I need to put feature vector, right? So please tell me ionic radius of what? Average ionic radius. Okay. So I will do average ionic radius. How do I take average? So basically, should I take concentration, composition weighted, average I will take, and that's how I'll do this thing. Okay. What else? There were a few other things. So atomic weight. So this one also I'll have to take averaging, or should I take full average? So whenever I am writing average, it's sort of understood that I am talking about composition weighted. Okay.
Even we are taking composition weighted average, it's necessary to include composition itself.
We should, are you saying to include composition? Yeah, so if you think about the last exercise, we included just composition, right? Atomic fraction. So composition, atomic fraction. So that also you can use. And this will also be, in this case, it will, the first case, it will have to check 5, 6, 11, 4, 15. So 5 by 15, so 0.33 aluminum, then 2 by 15 chromium, and then so on. Okay. Okay. What else? Very good. So electronegativity. This one also I need to take average. What else? Thermal stability. Okay, so thermal stability, melting point. Okay, so now melting point, how should I take it? I'll take melting point of the alloy, individual composition. So let me write two things, melting point of alloy and then okay, both I have written. Okay, which one do you think will be better at estimating? Okay, first of all, why melting point is important? The higher the melting point, the more stable you expect, the more harder it would be. Okay, at the end of the day, bonding is more stronger, and that's how you expect the hardness to be higher. Okay, so this is where the mechanism is coming into place, right? Some mechanism, some domain knowledge is coming into place. Okay, we'll discuss the difference between these two in a little bit. Okay, what else?
Actual hardness of the individual elements should be considered.
Hardness of the individual element. Okay, what else? Young's modulus. So now what I'll do is I'll put all different types of mechanical properties. Okay. What? Thermodynamic transition between what to what?
If this given alloy has any transition temperatures,
So, but you need to again put it in form of some feature, right? So, yes or no, do you want to put yes? Yes, it shows, or how do you want to put it?
either it shows, if it shows, then what temperature?
Okay. What if it shows multiple transformation temperatures? Say you are talking about aluminum will only straight away melt, right? It will go from FCC to it will straight away melt. But then in some cases there may be one transformation temperature, in iron it will be 2, 3 transformation temperatures. So now you need to decide a common way how you can featureize it.
Yes, if it is yes, if you go to one side and then compare it to transition.
Okay. So then in that case, remember our features are a m dimension, like I defined my m first. Okay. You cannot have variable number of features for different systems. Okay. So somehow, even if this thing you want to do, somehow you need to come up with a strategy wherein the number of dimensions of the feature is constant. Okay. So in your case, the way you need to do is you look for the element which shows the highest number of transformations. Say there is an element that shows 6 transformations before melting. So now you take a 6-dimensional feature and you, for each 6 dimensions, you record, okay, these were my transformation temperatures. For the second element which shows no transformation temperature, you just simply put 0 or you put some value there. For the third case where it shows 2 transformation temperatures, you insert first 2 and the remaining will be 0. So this way you will be able to still put this information. But it's a very complicated feature, I don't want to put on the board now. Okay, what else? We are missing,
Conductivity.
Okay, conductivity. Why conductivity?
Because cumulative of individual conductivity may result in a different conductivity for the alloy.
But we are talking about hardness only.
Okay.
Density.
Okay, density. So what about density of elements or density of alloy? Okay, now people are getting more creative. So now they are starting to include computational data as features also. Okay. So what if I write DFT energy, right? So DFT energy, what do we usually denote? E. Okay. So do you want for the alloy or do you want for individual elements? Okay. What else? Crystal structure. Okay. So crystal structure of the alloy. Okay.
If you have a DFT data, then we have atomic forces also.
Yes. So by forces, if you are talking about equilibrium structure, forces will be 0.
Let's say we are doing DFT.
Even in DFT, say you are looking at aluminum, FCC equilibrium, then it will be 0, right? All forces have to be 0. Otherwise, then you are not talking about local optimum, that optimal.
Activation energy for the
Energy will be non-zero, that thing will be 0, forces will be 0. Lattice, so crystal structure has it, that information. Yeah. So we mean crystal structure and associated features. Okay. Maybe space group you will represent, or maybe you can represent in terms of the symmetry elements which are present in the space group. Something like this you can represent. Or it could be as simple as BCC, FCC, HCP. Yeah, atomic coordinates tricky, we'll skip for now. Yeah. Very good. Electronic configuration, why do you say this?
For individual elements, the valence electron will be different.
Yeah. So say d electron, especially 3D, d electron configuration is very important. So now this electronic configuration you want at an alloy level or individual element level? Okay. You can also look at electronic configuration of the alloy through DFT and so on. Okay. So both are possible, but which one do you want? Both or? See, they have already gone at the alloy case and looked. You have already done this and you have the electronic configuration, right? Yeah. So I will put one is average over elements and then same thing at an alloy level. Okay. Okay. Now let me give a little bit direction. You have to think like metallurgist. Okay, very good. Grain size first. So that I think is covered here. Processing conditions. So basically say heat treatment and things like that, right? Okay. Still, I think let's see. Have we covered what are the rules that come to your mind when I say alloys? Hume-Rothery rules. Have we covered all of them? Valence electron concentration is sort of there. Valency. Okay, so sort of there, sort of not. A little bit slightly different form is there. Valency, structure. Then what else? Electronegativity is there. Anything else? Ionic radius. We didn't have. Do we have? We have. Okay. Okay. I think it's enough for discussion. So now we have to remember. Now we'll go one by one and say whether these are good features or not. Okay. What do we have to keep in mind? Are we able to make predictions for new cases and then screen candidates? Okay. So atomic fraction for the second, whatever case it is, I will be able to quickly compute atomic. Let me add one more thing. Okay. Rather than saying atomic fraction, I'll add one more thing, which is just the coefficient here. So stoichiometric coefficient, I think that's the way to say it. So this coefficient also I have added. Okay. Let's start with this. What do you think? Can I have this coefficient? So for example, 5, 2, 2, 2. Can this be my feature? Yeah, so this just like this, just I will preserve the order. First aluminum, then nickel, then cobalt, then chromium, iron, then copper. So I'll preserve this order and then only I'll write it. So then is it a good fingerprint? Yes. Okay. How many of you say no? I know one person will say no. So my okay, what about if I write this is my new alloy? Feature is new, feature is different. Is it a new alloy? No. Okay. So there's a lot of redundancy in this form of representation, right? So this is not a good idea. However, if I go to, someone said it already, normalizing it, meaning I go to atomic fractions, then I will always, it doesn't matter exactly how I'm writing my alloys in my data set, my feature will be unique or normalized with respect to my atomic fractions. Okay. So in that sense, this is a good feature, but this may not be a good feature. Okay. Yeah, so processing condition is there. Why this one will be bad? The chemical composition is same, but processing conditions are different, and so the hardness will be different. So that is correct. We'll come to this point. Yeah. What about, yeah, let's go this now. One hot encoding. What do you guys think? Good or bad? So why is it bad?
So we cannot consider like multiple aluminum.
You are the only one who.
No, I was telling
Somewhat
something similar like one hot encoding.
similar like one hot encoding.
We consider like not like 2, 3 also. Like that was my statement.
So then this becomes same as atomic fraction.
Yes, that was my initial statement.
Yes. So now, but okay. So we are all learning, right? So one hot encoding plainly it's not good because just knowing aluminum is present, yes or no is not enough. I also need to know how much aluminum is present and how much chromium is present. Okay. So just having one hot encoding, not important, but atomic fraction, right? Just also accounting for how much something is there. Okay. Okay. Let's consider this case. Or we can consider this one. Crystal structure.
The atomic fraction, if one of the feature is 0, what will happen?
Nothing, it will learn that it's a vector, right? Some parts of vectors are 0, some parts are non-zero. In fact, go back to the tutorial we just did, you will see some parts are 0. Okay. Crystal structure, is it a good?
Yes, because a lot of the properties will depend on.
Okay. So, is anyone think it's not a good feature? So, there is a crystal structure of the alloy. I want to scan through millions of alloy composition. Will I be able to get crystal structure of millions of compositions? Millions of alloys? How will I have access to this feature? Not even DFT, not even DFT. XRD I can get, you are right. Will I be able to do XRD for millions of cases? So we are still not in that world. Okay. So although in principle it's a good feature, yes, crystal structure depends on the property. I mean, hardness will depend on this crystal structure, but I do not have easy access to it. I want to use the model to make predictions. Unless I have access to the feature, I will not be able to make prediction for a new case. Okay. In case you have a database of crystal structures lying around and then you want to use it only for that data set, then it's okay. Okay. But this is a property which more or less you will not have access to. Okay. So in that sense, it is not a good feature. Same argument, let me commit here. Okay, I want melting temperature, I want to put melting temperature of alloy as a feature to the model. If I have melting temperature of the alloy available to me, it is simpler to go and measure hardness than to measure melting, right? So, I mean, in that sense, again, this is not a good feature for me to make the model. Okay. But again, if you have lot of melting data available to you and then you want to use that to make and also you have to remember, for a new alloy, this information should be available to you. If that is the scenario, then you can still go ahead and use it. Okay. What about these individual element? Individual element, I will always have melting data available. Okay. Unless you are talking about some nuclear elements. So there are few nuclear elements for which it's not easily available. It was surprising for me also. So more or less for the alloys cases we are talking about, this information will be available to you, and I can always average them in a composition weighted manner, or there are few other tricks to it also. You can do it and then you can use it. Okay. So if I am able to use melting, then I am obviously able to use ionic radius. So this also is a good feature. This one is atomic weight. Yeah, whether you use atomic fraction, atomic weight, I think it's not much different. So this one is also fine. Electronegativity, I have electronegativity tables available to me. Pauling's one is out there. Okay. In fact, there are multiple types of electronegativity. You can choose to put all of them. Okay. And why this should be an important feature, you know from your mechanism, you know from your Hume-Rothery rules. Okay. Conductivity of alloy, I don't have access to. Conductivity of individual elements, not sure if it's important or not, but go ahead, you can try it. Okay. But from a feature perspective, this is still something that you can use. Different mechanical properties, as long as you are averaging them at an elemental level, they all are fine. The moment you go at an alloy level, they are not fine, because for a new alloy, you will not have access to them. Okay. Density of alloy, not available, right? In most cases, it will not be available. Density of individual elements available. DFT energy, so that is a good, I mean, that's a good thing to consider. So what do you think? Is it a good property or not? Yeah, unless you know the crystal structure, you cannot talk about it. But I can say that I'll only talk about FCC. Okay, FCC crystal structure energy, that is my feature. Then I can calculate it. Now it will come down to how many calculations I can do, right? Because DFT energy is also not just very inexpensive to compute.
Not necessarily all alloys will settle in FCC.
Not necessarily alloy will settle in FCC also. But let me make an assumption that I will take 2 or 3 energies, because mostly they will either go to FCC, BCC or HCP. I will take all 3 energies and then I will talk about the hardness. Okay. So now it comes down to whether you have computational power available for the candidate set, for whatever your new alloys is, do you have computational power available to do that or not? Okay. If you have, then it may be a good feature. Okay. So adding computational data as a feature is also good as long as you are able to create features for new cases. Okay. And combining experimental and computation, this is how you can do it to actually improve your model performance. Okay, electronic configuration alloy, again depends whether you can do computations or not. And average electronic configuration is anyway good. Okay. So,
I have one question.
yes.
If you look at the DFT energy you're talking about, like earlier, we are able to correlate the hardness with energy with other elements. It's just like simple, go with simple, like pure elements like aluminum, copper, and going gold and everything. Have there been any relationship with the DFT energy and the hardness?
I mean, I have not checked it, but I will assume that it will be there. Because in a bulk material, you have, say, I'm talking about aluminum bulk. In an alloy, I have both aluminum as well as aluminum, copper, whatever, right? So both, so part of the interaction is present in the bulk and a part is present in the alloy. So there is some overlap. Okay, so I hope this exercise was useful and
Are you talking about formation energy or the total energy that you get?
you can use both. I mean, whatever in the way you want to define it, you can use it.
You consider total energy for the two systems, like it double the system size, make a supercell. You have a
Yeah, okay. So in that way, it should be energy per atom. You always want to normalize it with respect to per atom. Same for formation energy also. Whether you're talking about 1 mole formation energy or 10 moles formation energy, right? So we always have to do per something. Okay, so now just revisiting this one, what I want to say is that elemental properties, these are good things, these are good starting points for you to start making your features, because you can take average of ionic radius, electronegativity, their individual melting point, boiling point, individual densities, whatever. Individual element, all properties are available. These are good sources for features of different materials. Okay. Yeah, and then this is one paper in which they actually made, is this the same paper that we referred to in the tutorial? And these are the features that they used. So not only they use the composition, not just the elemental properties, they also use this atomic radius difference, electronegativity. This, you can also use CalFET. So we talked about DFT, but we have CalFET also as a thermodynamic modeling, thermodynamic model available to us. So you can talk about mixing enthalpy, configurational entropy, okay, shear modulus, bulk modulus. These are the other things you can talk about. Okay, so these guys use these as the features. Okay. At a higher level, now just to give a little bit of structure, there are 3 levels of fingerprint you can actually talk about. Okay, the first is the higher level. Whatever we have talked so far is actually at a higher level, meaning we are using some other properties to talk about another property. I use ionic radius, electronegativity to talk about hardness. Okay, so some other physical properties to talk about another property. I can also go at the atomic level. Okay, meaning I can talk about what are my neighboring atoms. Okay, in this one, in the first case, we never talked about what are my neighboring atoms, right? We never went at the atomic level. And then there is a even finer level in which I am talking about exact, not just which is my neighbor, but also how far is my neighbor. Okay, so distance, bond distances, bond angles is the most final or the atomic level. Okay, so broadly these I will use as a structure. I mean, there is no a good demarcation between them. They always have some overlap, but just to give you a little bit structure, these are the different levels of fingerprint we can talk about. Okay, And then there is always this miscellaneous category which creative, you come up with another way of fingerprinting which is outside any of these domains. So high level fingerprints, what can it be? Whatever properties you can think about, right? For an element, I can think of different physical properties, density, grains. Actually, we missed these two. Okay, yeah, let's cover this also. So grain size, although it is very important, but will I have access to grain size for a new alloy? We don't have control over it, right? Processing conditions. I can think of my processing procedure, right? And for all the alloys, I will use only the same processing procedure. Okay, so this you can define yourself. So from that perspective, you can still use it, given that for the alloys that you have created, you already have the processing condition. So for your training data also, this information should be there. And in this particular example, this information is this information can be available for the candidate data set for the new alloys, but may be absent for the current data set that you have. So processing conditions of alloys, you will check. If you are in the alloy community, everyone is making them in a different way, right? So, and no one is reporting it well. So processing condition is something that for training data is not available. Okay. And then there was this question about atomic fraction and processing condition. I mean, you can have same chemical composition, but if the processing conditions are different, the output will be different. In that case, what you have to do is you have to concatenate your vector, meaning you not only have to use your alloy composition, but also your processing conditions together to talk about model development. One part of the model is talking about chemical composition, the other part is talking about processing conditions. Okay, so coming back, high level fingerprints, I can use different physical properties, thermal properties, okay. So heat capacity, from different thermodynamic databases you can get this information. Electrical properties, conductivity, band gap, dielectric constant, and whatever at an elemental level you can think of, you can put that as a feature. So this is just one example I am giving. In this case, the authors were interested in predicting intrinsic electric field breakdown. Okay, so what is that phenomena? Same as what you see lightning, right? You basically, this is a breakdown. Air is insulator, and then when lightning strikes, basically the air becomes conductive because there is a breakdown that is happening. Okay. Now, if you want to design features for it, what will you have to use? You first need to know what is the mechanism of breakdown. Okay. Just like for hardness, you know Hume-Rothery rules are there to help you. Similarly, you need to understand the mechanism of the breakdown. So the mechanism of the breakdown is that electrons, because of the high electric field, they gain kinetic energy. That kinetic energy is given to the phonons, basically to the atom structure, lattice. And if the rate of increase of kinetic energy of the electrons is higher than how they dissipate their energy, then breakdown will happen. Okay, so this is the basic mechanism. Now, if you know this mechanism, then you know it is important to talk about phonons, it is important to talk about electrons, their kinetic energy, band gap. These are the important features that are associated with my mechanism. And once you understand that, you will see that these authors have considered properties which are related to that mechanism. So for example, they talked about band gap. The larger the band gap, the difficult it is for electrons to have high kinetic energy. There won't be any free moving electrons. Phonons related frequency. So phonon electron coupling. These are the things you need to talk about to capture this phenomena. So once they knew this, then they go ahead and train the model, and then they were able to make good features. For such a database, if you go at density and these things, it may not work out, okay, because you are not directly capturing the underlying mechanism. Okay, then what now coming, I mean there is a huge range of properties we can talk about, right, for at an elemental level. We can keep on going, okay, and that is where Kamal comes into the picture. There are a few readily available platforms which will allow you to quickly make features for your database, okay. So Jarvis I have mentioned here. Similarly, there are a few other packages available through which you can make such elemental features for you. Okay, any questions here? People are generating? RDkit they are using, okay. So we will molecular level fingerprints, right? Yeah. So we'll cover them. So I'm just giving now some examples where people have used this higher level fingerprints to make, to learn properties and so on. Just to give you a flavor of the diversity of things people are doing. So this one is on superconductivity, this one is on thermal conductivity, this one is about bulk and shear modulus. Okay, so different range of properties people are learning using similar concept of models. Okay, we'll talk about the limitation of these models once, but okay, this I don't want to touch. But let me just give a little bit more detail about the shear modulus. And so in this case, the shear modulus and bulk modulus study, the important thing was the data that you see here. You see the ground truth is actually DFT value. So the authors did not have access to experimental data. So what they did, they had lot of computational data available to them. They trained their model on computational data. They used the model to make predictions for new cases. So this is how they make predictions for all new cases. So what this model is predicting, it is giving you an estimate of DFT computed bulk modulus and shear modulus. Okay. But once you have done this, then they selected two compositions which are giving high bulk modulus and shear modulus at the DFT level of theory. Once that is done, they went ahead and did experiments on it, and then they found that these are indeed showing, I think they call it super hard materials. There is a special ultra hard materials. I think there is a term for it. And they found that actually the hardness of these alloys is, I mean, of these carbides. These carbides are indeed like very high as compared to some of the known inorganic materials that we have. Okay, so see how people are being creative, right? They don't have access to experimental data. They use DFT data, but from DFT data they were able to screen materials, and for those they were able to do experiments. Okay, so the information flow can happen in any way.
Where I could find this sort of data? Is there some verified data set?
Yeah, I think like the Jarvis data set they talked about, I am sure in that you will see. I think I do know materials project does have information on elastic constant matrix. So through that you should be able to find. Okay, one more interesting thing here. I asked, so I was a part of one of the conference where these people were presenting this work, and then I asked them how much time it took you to make the model versus to make the measurements. Okay, so they said that overall around 3 years it took them to complete this study, out of which 6 months were on machine learning model training and 2.5 years were on just making the material and being able to make the measurement. Okay, so this is why we use the term accelerating materials discovery, right? Within 6 months you are able to screen it, and your time of experimentation, although it is still long, but at least you are not wasting your effort on those cases which might have not have resulted in good prediction. Okay, yeah. So now let's move on to the second level, which is a molecular fragment level. Any questions? We are running a little slow. Okay. So this one I'll try to do. This is how a polymer database may look like. In polymers, you can represent them using something called smiles. Okay. So smiles is nothing but it's a textual way of representing polymers, okay, or even monomers or molecules. So for example, this is my first polymer, and this is what it represents. So basically, it represents ethylene, yeah, polyethylene. So you have carbon repeating, okay, that's what it is representing. Okay, and then this is how the second one is, and for a more complicated case, this is how. So where the stars are representing my connecting units, okay, where the connection should happen. And then the question will come, just like for alloys. Now for the alloys case, I had alloy compositions and then hardness. Now I have polymers and then their band gap. Okay, so how can I do fingerprinting for these cases? Okay, so in this case, in the interest of time, I'll not go on the blackboard and ask you to help me here, but we'll just directly go how people do it. See, one good thing about organic materials is that you sort of know that this is how the bonds will be. Okay, covalent bonds, they are well defined. If I am talking about oxygen, it will form some double bond with something or two bonds. Okay, valency of oxygen is known. Carbon, 4 bonds it will form. Okay, either it will be in sp3 state or sp2 state, sp state, whatever, but one of these state it will form the bonds. So there is this structure available, which is not available for my alloy case because they are random mixtures. Okay, so now because this structure is there, I can exploit this to talk about my fingerprinting also. So for example, in this case, what people did was they simply looked at triplets. What triplets are present in my polymer? So for example, what it means is triplet meaning element A, B and C with coordination of I, J and K. So for example, C3S2, C3. C3 means carbon is having 3 bonds. So it is in sp2 state. Okay. S2 meaning sulfur is having 2 bonds, both should be single bond, and then C3 again means that 1 double bond and 2 single bonds. Okay, so coordination of carbon should be 3. Okay, in this case H1N3C4, so hydrogen will obviously be 1. NS3 meaning there is no double bond associated with nitrogen because all 3 bonds are available, and C4 means that carbon is also all single bonded because 4 bonds are available. Okay, so this way they came up with different fragments and they just simply checked whether a particular fragment is present or not, and this is their fingerprint. So this thing is a little bit similar to one hot encoding that we talked about. Okay, but this is one hot encoding at a triplet level. So you will look at triples and the coordination number is also defined. Okay, so for example, if in this case, if the nitrogen was double bonded, then it would have been H1N2C4. But if nitrogen is double bonded, then it should be H1N2 and C3 because then carbon will also get double bonded. Okay, so and then the fingerprint is simply whether a fragment is present or not. Okay, this is a simple way of fragmenting them. Now, if you think about it, the total number of such triplets will be large, right? You can come up with several triplets. So they looked at a good level of library, say some 800, 900, whatever. I don't remember the exact size, but somewhere a couple of hundreds is the feature size. One more thing you may want to ask, why not just doubles? Why did they go for triplets and why not for quadruplets? Okay, so that is where we are not ready yet to talk about it, but there is, if you go to doublets, then I'm losing information because I'm not covering that many neighbors, and if I go to quadruplets, I will have lot many quadruplets, the feature size will be much larger. Okay, so either way going is there is a trade-off. Okay, that's why triplets worked out to be the best. So let me ask you this, say I have one fragment like this, the other one like this. Are they different or are they same? Same. So whenever making features, I need to make sure that I'm not double counting. Okay, they are actually same because I'm just counting yes or no. Okay. Now that's where another this thing comes. Do you think this fragment is present as part of this molecule? So this will be C3. This one is O1 and you can take either one as C4 here, right? So this is present. Now that's where the next question comes. In here I have a ring, but I can have a linear counterpart also. In both of them, this fragment is present. So now how do you distinguish whether this fragment is part of linear thing or part of a ring? Their properties should be different, right? So how do you distinguish?
Both those pairs will occur in the same structure.
Yeah, so meaning at least at this feature level, I cannot talk about it. At this feature level, I might not be able to distinguish them. Okay, if the ring size is less than 3, then maybe yes. But if the ring size is larger, then I will not be able to distinguish them. Okay, so this is the limitation. So see any feature you take, it's not that it's perfect. Okay, so this is another limitation that we have to just be aware of.
Order of the feature can be.
Order has no relevance. That's what.
We take that, we take before the IU5 numbering, then the reverse C4, C3 one will in fact close the ring.
Ordering has no relevance, right? Whether this fragment is present or not is what we are asking.
In the same.
Okay, we'll talk later. Okay. Okay, so now because these limitations are there, what they did was they not only look at these triplets, they added few more higher fragments which they call as block level. And then if you know polymers, there are much more larger length scale mechanisms that are happening. So for example, length of the side chain tells a lot about what will be the glass transition temperature. So for that, the fragment length should be extremely high for you to capture it. Okay, but you cannot do that because then your dimensionality of features are extremely large. So they added a few more different levels of features to make it more comprehensive and complete. Okay, so this is one way how people have been doing polymer fingerprinting or even organic fingerprinting, whether it is molecules or polymers, both people are doing in this manner. For ligands, ligands also you can represent through smiles, right? So same, whatever you can represent through smiles and through this way, you can do that this way. Okay, so now unfortunately this is not open source because now it's a startup, so they want to earn money. Okay, but they have done actually wonderful work in this area. It's not visible, but they have all types of properties, electronic properties, dielectric properties, mechanical, solubility, permeability, whatever. Whole range of polymer properties they have learned using this similar scheme. Okay, so now there is another popular open source fingerprinting technique, which is basically Morgan fingerprints. I think someone was talking earlier. So in Actually, this is also very similar. You just need to count the fragments. Okay. So in this one also they do the same thing. They look at fragments, but fragments, this fragment is of length 3, this fragment is of length 2, this fragment is of length 5. Okay. So fragments of different lengths they are counting, and they are saving it in a more efficient manner. So what you can do is, there is something called as hashing function. Basically you check which fragments are present or not. Ultimately it becomes 0 and 1, something like one-hot encoding, whether this fragment is present or not. That you compress into a bit vector. So once we do the exercise, that's when you will see it. Okay. So at the end of the day, this is also just counting whether these fragments are present or not. That's all. Okay. We can go on and on. There are so many other fragments basically counting. So like you can see here, right? You can count something like, let's see. So this one is surface area, okay, free surface area, volume surface area. Log P is about hydrophobicity. Okay, there are so many different fingerprints that people have come up with, and you can also see the years. Okay, so not recent, somewhere about 20 years ago, that's when people were working a lot. So this whole space is called chem informatics. So people have worked a lot on developing fingerprints to develop for molecules, and same things people are expanding it for polymers also. Things that I wanted to discuss, but I think in the interest of time I will not have, I'll have to quickly go through it, is something called this chi values. And the reason I'm emphasizing on this is because these are also graph based methods. So I think Pawan talked about it. We did that exercise yesterday wherein we represented structures in form of graphs. Same way you can think of these molecules, polymers, as graphs, and then you can start extracting and talking about features of this graph. Okay. And in this work they precisely do that, and the way they do it is, there are some equations here, but simply say this is your graph. Okay. Atoms here, so this is my carbon atom, this is my carbon atom, carbon atom, carbon, carbon, carbon. Okay. For these atoms, these will be my nodes, and edges are basically the bonds between them. What I do is I simply count, okay. So I will simply count. So one thing you have to understand, these are carbon atoms here. It's understood. And hydrogen atoms, depending on what is the valency left, everything else is hydrogen atom. It's understood in this representation. So how many neighbors does this carbon atom have? Non-hydrogen atom neighbors. 1. This one? 2. So 2, 2, 2, 1. What I will do is, I will do inverse and then square root. Okay. So inverse of square root is same 1. This one will become 1 by root 2. This is also 1 by root 2, 1 by root 2, and then this is 1. Okay. I sum all of them. This is my one feature of this graph. Okay. Next time what I will do is, so if you sum it up, I think, okay, we'll see it. Next time what I'll do is, I'll take these two and then I'll talk about this bond, which will be nothing but multiplication of these two. So this will become 1 by root 2, this will be 1 by 2, this will also be 1 by 2, this will be 1 by 2, and this will be 1 by root 2. I'll sum all of them. So this is something like degree 0 summation, this one is degree 1 summation. Now next time what I'll do is, I'll go degree 3, wherein I'll talk about these two bonds together. So how will I talk about these two bonds together? I'll multiply this, this and this. Next I'll talk about these two bonds together. How will I talk about it? I'll multiply these three things. Whatever I get, I'll sum them up, and this is my second degree of representing the graph. So I think it will become easier here. So this is my 0th degree, where I just talked about that particular value. First degree, I'm talking about different edges. Second degree, I'm talking about 2 edges simultaneously. Third degree, more, and so on. This is another way how you have converted a graph into a set of numbers. Okay, so see the progression. We started with atoms, telling them what their feature is, and then we multiplied bunch of atoms together at different degrees to get a series of number, just not one number, a series of number, and all these series of numbers collectively represent my graph numerically. Okay, and why I am emphasizing this is when we talk about graph neural networks, it's actually people who understand graph neural networks are actually doing the same thing. There is a message passing happening which is done in exactly the same manner. It's just that this definition of how nodes should interact is a little bit ad hoc. In graph neural networks, this definition is learned. Okay, here we are specifying in graph neural networks it will be learned as part from the data. Okay, and then there is this finer atomic level fingerprints which Kamal will cover tomorrow, so I don't need to talk about it. Okay, so should we quickly go through the notebook file? So again we have some Python libraries, scikit-learn model, but more importantly we have this RDkit library. So RDkit library is that open source library that allows you to compute fingerprints for different organic, either molecules, polymers, and so on. So the graph-based fingerprint that I talked about, you can compute it through this RDkit library. The fragment Morgan fingerprint that I talked about, you can also compute that through this RDkit. There is a whole series of fingerprints that you can compute using this RDkit library. Okay, and then running this code will allow you to install that. Okay, and then what we are doing is we are basically reading polymer data from another paper which has been referenced here. Okay, so this is the paper from which we are reading the polymer data set, and the way the data set is given to us, it basically is a very comprehensive data set. So roughly we have 1, 2, 3, 4, 5, 6, 7, 8 properties are given to us in that data set. Properties like atomization energy, band gap, electron affinity, ionization energy. So different values, computed values of polymers is available to us, and the numbers here denote how many such data points are made available to us. So for example, EGC, I think it's the band gap of polymer chains, about 3000 data points are made available to us. Okay, and the form in which the data is available is this Miles format. Okay, so remember, you can always represent these organic molecules in this Miles format, which is a textual way of representing these molecules. Okay, and I'm doing a few things, not important, I'm just focusing on 2 properties, so you can check that part out. But more importantly, I wanted to show you this, which is that using this library you can also visualize that these are the molecules I'm talking about, and then what are the values available. Okay, in some case NaN is being printed. So the reason being, obviously if I have 3000 EGB values available to me, but very few, I think maybe it's the other way around. It's more like that for all polymers, all properties might not be available. Some may be missing, right? So that's why some are NaN. and then I'm just focusing on a particular smile. So say I talk this particular polymer. For this polymer, this is how the different, this is how RDkit is storing it basically. So it is storing, this is the atom the index, and this is a sulfur atom and so on. Okay. And this is where the things get interesting for us. One of the strategy of fingerprinting was that Morgan fingerprint, right? And this is how a Morgan fingerprint for that molecule looks like. Okay, it is very similar to a one hot encoding, some ones, some zeros, right? It's a string of one hot encoding. What does one mean here? It just means there is a particular molecular fragment that is present. 0 means there is a particular molecular fragment that is absent. Okay, simply just checking whether molecular fragments are present or not. So now we can try and understand what this 1 and 0 mean. So that's where you can even visualize. So I can visualize those parts of the Morgan fingerprint which are 1. So basically which fragments are present, and this is what you will see. So basically what it is saying is that carbon which is 3 coordinated is present. Okay. This type of motif is present, and then this type of motif is present, this type of motif is present. So basically it's just saying that okay, these motifs are present. So basically that fragment is present. That's what the fingerprint is all about. Okay. And next what you can do is you can generate this fingerprint for all polymers that are given in your data set, and this is the way you have a feature available to you. So once the feature is available to you, the property is available to you, you can start using your linear regression model or any other machine learning model to start training the data. Okay. We are getting some depreciation warning. I think this is where the version things come into picture. Earlier I was using, they might have updated the version, so that's where this warning is coming. Okay. But in terms of results, nothing has changed. So in this case, what you're seeing is, so finally this is how the data set would look like. So these are my different polymers, around 3000 polymers, and then I have 1024 dimensional quantity just consisting of ones and zeros, which are telling me the fingerprint of my polymer. And then what I've done next is, again, visualize your data, start training the model. In this case, I am using a random forest regressor. So this part maybe Kamal will cover tomorrow, where he'll talk about different types of machine learning models. And once you use, and then again I'm using cross validation. So we discussed about it, how we can talk about the accuracy of the model. So we have this cross validation accuracy, and then finally you can see that I'm getting an R2 score of say 0.83 and RMSE value of 0.64. Okay. That I think section 6 is something I'll not recommend you guys to go as of now, because we have not done feature engineering. Okay. But there is some things you can do to improve the performance of the model. But something more I have done here, which is not just Morgan fingerprint, there are other types of fingerprint that RDkit also provides. So something very similar to, you have atomic fingerprints for alloys, and to that you concatenate processing condition fingerprint. Same thing I am doing now. I have Morgan fingerprint, to that I am adding my graph-based fingerprints, and I am making an even longer fingerprint vector consisting of both these different types of fingerprint strategies. So these are some other fingerprints that is being added. So these all graph descriptor based fingerprint is the same that we discussed on board. So once you add that, and then again you go ahead and make your models, what you will see is that the models actually perform well and the cross validation errors are even lower, and the R2 score are even higher. So in this case, combining your Morgan fingerprint along with different graph-based fingerprints and some other RDkit fingerprints resulted in even more improvement in accuracy. Okay, yeah, I think that's all I wanted to cover. Thank you guys. Thanks a lot.